Again, my talk is also centered on color image processing. So here I will give some examples of color image, color enhancement and color dispersion algorithms, which we have developed in the DCT domain. So before that, let me just give you some fundamentals related to the some introductions on color representations. You know that actually, physically, if we say that the definition of color is basically it's the wavelength. It's the wavelength of the electromagnetic radiation. It's a particular range of electromagnetic radiation that is perceived as optical sensation, and each wavelength is associated with a particular color. But in our so when we consider how the color is generated when in the images or in a photography, you consider an illumination of the same, which has also the component of different wavelengths of the color, and the object which is being illuminated. So while the light is falling and it is reflected, so it's a reflection which we are considering in this case for the color generation. And that object also has different reflections for different wavelengths. Okay, so it basically it reflects different amount of energy depending on the incident ray. And this is the material property of the object. So it's an intrinsic property of the object. Illumination. This spectrum is also intrinsic property of the illuminator or the light source. So these two determines actually the color introduction. So if you are multiplying these two and then you are getting the color sensation. There is also another added thing which is okay. So this is what is there. That it is the product of the spectrum of incident light and the reflectance or light absorption. Right. So finally, you get this is the color stimulus from an object. Okay. But the other thing what I was talking about, that what is the property of the detectors? Okay. So in our human perception, we have the biological detectors. We have these cone cells, rod particularly cone cells. They are responsible for chromatic representation. And there are different three types of cone cells that is being finally well postulated and later also I think mathematically it has been also proved. Each one has its detection in its own range of own optical range, and depending on that, you sense the color. That means depending on that, actually colors are produced. This computer is little slow actually. Fine. So as you can see, that colors are generated through three responses, and I think these are almost view that we have that we have more green cells and so finally a color is represented by three different components of three components of this kind of detection, because you have three different types of detectors and each one is giving you three different stimulus, and as a combination of these things you are sensing our color. And this is what is that additive color mixture model. Of course, human reception has a peculiarity that actually there is an experiment. Experimentally, if you would like to match our sensation of colors with a different kind of wavelength, we'll see that with a particular, with this kind of responses at particular wavelength, you have negative responses. So this problem actually is mapped, is resolved by taking, it's not resolved, it's basically modeled in such a way that actually you get all the positive responses. And this is also one of the reasons why that all the primary colors, I mean, a set of primary colors cannot generate the positive. I think this is, I'm not, I have to a little bit hurry up, so I'm not discussing that. So finally, these are the factors when you sense color. Like you have the intensity of the perception, intensity of the color. Then there is hue, which is representing the mean wavelength of the spectrum, and there is saturation, which is the standard deviation of the spectrum. Now, these two factors, hue and saturation, this is a major factor for, these are the major factors for color vision or the chromatic sensation. So this is what is the dominance, these two represent the dominance part, and intensity represents the usual achromatic vision by the gray level part. There are certain limitations of price-stimulus model, and in RGB also we have these limitations. We cannot really correlate with its physical, with the physical, the significance of a color. So given an RGB value, we need to map to certain wavelength of the actual physical wavelength of the optical range, where actually it should provide the hue, and also simulate the sensation value. So for that, actually there are different color spaces are proposed. One of the color spaces is CI XYZ, and in fact this is the space which is rather, it has standardized the color perception models, and with experimentation it has charted basically the points in the chromatic space and also the corresponding waveform. Like this is a transformation, it's a linear transformation, and this is the chart. We see that if we move around these boundaries, this is the chromatic point, and as you go radially, actually saturation increases, and the boundaries are representing, these points are representing the color corresponding to particular wavelength. So you will find that these wavelengths are higher and these wavelengths are lower. So that represents a particular color. So this figure itself shows different types of colors being displayed here. And this is the color chart. So given so this is one simpler way of representing a color or correlating the corresponding chromatic